Dear viewers, welcome to IMTMA's E-Train module on geometric dimensioning and tolerancing, GD&T in short. The key objectives of this E-Train module on GD&T is to take you through an introduction to GD&T, the need of GD&T in engineering drawings, the 5 groups of GD&T parameters, the hierarchy of GD&T implementation, then a clear understanding of MMC, LMC and RFS conditions, when each condition would be applicable, then the meaning of bonus tolerance and its advantages, then datum reference frame DRF, how primary, secondary and tertiary datums together constitute a DRF, and how degrees of freedom are constrained by a datum reference frame. Then we will be going through in detail about the 14 main parameters coming under form controls, orientation, location, runout as well as profile controls. After that, you will be pretty comfortable in interpreting drawings with GD&T symbols, and while we go through the individual parameters, we also will discuss on measurement and validation of each of the parameters. And also we will be discussing upon applications of each of the parameter with industry examples. Let us make a beginning. GD&T in short, it can be defined like this. It is a means of dimensioning and tolerancing a drawing by considering the function of a part and how the part fits with the other parts constituting a subassembly and the final assembly. It is called as, it is based upon functional dimensioning philosophy. To understand the need of GD&T, let us consider a simple example. In order to understand the need of GD&T and how it relates to the functioning of the parts in an assembly, let us consider a simple assembly consisting of 2 parts. One is a shaft of diameter 20 G6 and other part is a plate having a bore of dia 20 H7. My design requirement is that in assembly I should have a precision sliding fit between the 2 parts. That means I need to have 20 H7 G6, which precisely explains the requirement of precision clearance fit between the 2 parts in the assembly. Now the shaft dimensions are shown, and shaft is shown as part number 1 and length of 80 millimeter, head thickness of 16 and head diameter as 32, whereas the bore of dia 20, let us say the plate thickness as say 16 millimeter, and each part I am making 10 numbers individually, and I have 10 shafts with me and I have 10 holes with me. Now I am trying to assemble all the 10 pieces together, shaft as well as the hole. Now my question is, will I get the required 20 H7 G6 fit in all the 20 assemblies? What could be the answer? The answer could be either a yes or no, depending upon what is the form error and orientation error available in the individual components. Let me explain. Let us say the shaft is having a little bit of bend on the diameter 20 diameter. Instead of being straight, it is having a convexity or bent along the axis. Now, while checking for the diameter, there could be chances that at individual sections, the diameter I am getting within the stipulated tolerance of dia 20 G6. However, because of the bend, I may get into a situation the shaft will not enter the hole at all if the bend is too much, or if the extent of bend is within limits. I can realize a situation the shaft is entering inside the hole, but the degree of clearance all along the periphery is not uniform as intended by my design requirements. So that's why, in order to ensure the design requirement of having H7G6 fit in the assembly, I need to control the form error or shape error in addition to maintaining the size within limits. Similarly, there could be yet another situation where the dia 20 area is not normal to the face. The shaft is bent at an angle of say 1 degree or 2 degree, whatever it is. In this case, what could happen in the assembly is, again, I will not be able to get a good amount of seating area once the shaft enters inside the hole. In other words, I will have the shaft seated at perhaps at 5 degree, instead of having a surface contact, I will realize only a line contact or point contact, which will not answer again my design requirements and load bearing characteristics, etc. Therefore, in addition to the dimensional tolerances, we need to maintain the form and orientation parameters within control. That's why we say the entire tolerances can be divided into two groups. One group we can call it as dimensional tolerances, and the other group we can call it as geometric tolerances. Both need to be controlled in order to have the desired function in the proper manner. Let me take you through few more examples highlighting the need of GD&T in addition to dimensional tolerances. Look at this example on the screen. The part 2 has to have sliding movement over the two pillars of part 1. By studying this assembly, we can very well conclude the diameter of the shaft is extremely important, no doubt about it. But in addition to that, what is more important or what is equally important is the parallelism of the two shafts. What happens if the parallelism is not there between the two shafts? Again, with the free movement of the part 2 can never happen, as the two shafts are either diverging or converging. Similar to the parallelism requirement, we can keep on adding number of requirements in this example, like straightness of individual shafts, the perpendicularity of the shaft with reference to the part 1 base plate, etc., etc. Look at this assembly, which is nothing but a CD drive in any personal computer. Here also the motor axis has to be parallel to the seating surface of this CD, so that the reading and writing can have without any issues. Now look at this assembly of an injection mold, wherein multiple plates are there, right from bottom plate to top plate, through cavity plate, core plate, etc. Even here the parallelism of the individual plates are very critical. The alignment of the guide bush to the core plate and the alignment of the guide pillar to the cavity plate are important to have a uniform closing and opening whenever the mold cycle operates. Similarly, look at the third example, which is nothing but a machine tool spindle assembly for a vertical machining center. Here I have the spindle housing, then I have the spindle running through and through, and I have the angular contact bearings. Here also, when you consider the spindle, the straightness or cylindricity of the spindle is one of the important parameters. Then the run out of the individual features with reference to each other are important. The perpendicularity of the seating face with reference to the axis is again important. So basically it could be any assembly consisting of more than one part, where each part has to relate to some other part. So the form error and orientation of different features is critical in order to ensure proper assembly as well as proper functioning. So GD&T is very significant as well as extremely important, basically in all kinds of parts wherever the interrelationship becomes important within a part as well as from one part to the other part. In short, this slide talks about the need of GD&T. The first point we talk about GD&T makes the communication through engineering drawing uniform across the manufacturing organizations. I am sure all of us will agree engineering drawing is the language of engineers. As such, GD&T provides a universal understanding using symbols and the notations instead of writing verbal comments or instead of writing other means of notes. In other words, the designer's intent is very clearly communicated to all the downstream applications. It could be process planning, could be production, assembly, quality departments, etc. Without GD&T symbols, the drawing becomes subjective. That means if three different teams are interpreting a drawing, three different interpretations could be possible without GD&T. Whereas with GD&T symbols, the drawing becomes unique and it conveys the same meaning across different teams, across different organizations, etc. Then the third important factor is GD&T focuses on functional assembly. Once the GD&T parameters are maintained within control, the values, the assembly will happen without any failure, and the cumulative effects of tolerances will not happen as in the case of plus minus tolerancing. Then components with dimensions departing to worst possible situation will also realize in functional assemblies without any issues. So this is the particular aspect of position tolerance, which will be clear when position tolerance discussion is taken upon. Then one more important aspect of GD&T is datums are mentioned clearly in the drawing, and which helps in ensuring a uniform method of manufacture. That means the same part, whether it is manufactured in place A or place B or place C, again the interpretation is the same, and the method of designing a fixture, loading a component, machining a component, and inspection and validation of a component are uniform without any ambiguities. Thus, in short, we can say GD&T will ensure interchangeability across the millions of parts produced around the globe today. As all of us will agree, we are living